Welcome to this short course on quantum thermodynamics, and I will explain the fundamentals of the theory in a couple of 3 hours. So today will be the first class of this course, and yes, you might have read in the outline. Quantum thermodynamics arises when one tries to extend the ideas from classical thermodynamics to the quantum regime, quantum systems, and tries to analyze the energy exchange between the subsystems, system and environment, to analyze the entropic behavior, all the kind of stuff one analyzes in classical thermodynamics, but with quantum systems. This course will have a structure like we'll begin with the introduction today, very brief from a historical point of view, in order to motivate the topic of the course. Then I will explain some previous concepts, like density matrix and the implicit equation. This will be like 15-20 minutes. Then we'll move to the laws of the quantum thermodynamics, especially to the first one, and we'll also discuss a little bit the second one. I said we're going to discuss the second one briefly today because we'll move to the entropy production and the relation to the quantum information the following day probably. This will be a very interesting topic to discuss, and we'll finally comment a little bit about the applications of this theory, basically quantum thermal engines and quantum batteries. It will be also the following day. There are some references for the course. This will be the main reference for today's lecture, covering this part. And it's a very nice book. It was recently published last year, so if you want to take a look at it, we have a couple of copies here. We also will use the notes of Danny regarding the limited advanced equation. It's very well explained, and you can get all the details of the derivation of the equation. There are also many references. For example, the edited book by Binder, Thermodynamics in the Quantum Regime, published by Springer. You can download it here in the university. So, more or less, that will be the references for today's course. As you can see, I won't cover other topics like thermomajorization, quantum thermometry, quantum stochastic thermodynamics, resource theory, or the relation of quantum thermodynamics arising from an information theory approach. Those will be topics for other courses. I can provide you with references to cover that, but it won't be the main scope of the course. So yeah, it will be very basic, basically presenting the laws and the main applications to engines and batteries. Okay? So as you may know, thermodynamics arises when one tries to analyze systems as a whole, right? No matter the internal composition of them, you want to understand how it behaves in the presence of an environment, right? Okay, that was stated at the beginning of the 19th century. Especially from Carnot's book in 1824, followed by Clausius, people like Kelvin or Planck, right? Covered all the 19th century. In a parallel way, you have Boltzmann, who wanted to extract thermodynamic properties from the constituents. Right? So, analyzing, for example, if you have a gas, analyzing the movement of the particles and then averaging some quantities, he wanted to extract thermodynamic properties of the system. Yeah, that's done by statistical mechanics, right? Okay. One might say, okay, if we have some kind of approach to study this behavior of little particles, especially if you have a bunch of them and you can average stuff, why do we need to formulate a new theory of quantum thermodynamics? Okay, the main motivation is, can we just focus on one of these particles and treat this as our system instead of having a bunch of them and then averaging stuff to get thermodynamic properties? Let's take a single particle, quantum particle, and try to analyze how it interacts with the surroundings. That's the main motivation to study quantum thermodynamics. The first quantum thermodynamical operational paper dates back to 1959 by Scoville and Dubois. They proposed a 3-level amplifier and to act like a quantum engine. So if you have 3 levels, it will be the energy level 1, energy level 2, and energy level 3. And you attach this to a thermal bath at a temperature, cold temperature, and these 2 levels to another thermal bath at a temperature Th greater than Tc. This amplifier can operate by employing these 2 thermal baths and maintain the population inversion between these 2 levels. Between these 2 levels. So this can operate as a thermal bath. Doing some maths here, this would be the frequency difference omega c, and this will be omega h. So the ratio of the populations is given by a Boltzmannian distribution. That's pH over pg. This will be equal e to the minus the energy of that one minus the energy of this one over the temperature difference. Well, Boltzmann T3 minus T1. Let's call this the temperature of this T1, T2, and T3, which is the same as e to the minus h bar omega h. The case would be and that will be TH. Okay, we can do the same for these two levels. So we'll have PC over PG is equal to the energy difference over K sub B. Okay? So, if you connect these two levels to an external field with frequency omega, you can act this as an amplifier, right? We have a here and then a photon is released with a frequency omega, big omega. And this will act as a quantum engine where the efficiency of the engine, of the amplifier, is simply given by the energy difference of these two levels over the energy you are taking, which is h bar omega h, which is the same 1 minus omega c omega h. This relation is familiar, right? Okay, since one wants to get some population inversion, pH must be greater than PC, sorry, because otherwise you won't have this inversion of population. Then E to the minus h bar omega h of K sub B TH must be larger than okay, or the quotient of temperatures of the related to the cold level must be larger or equal than omega h over omega. Now, it is straightforward to compute one minus omega c of omega h will be less or equal than 1 minus Tc over Th, which is the efficiency of the Carnot engine, right? So you can get an operating engine from this amplifier, and the efficiency is less than equal than the Carnot efficiency. All right? This was the first experiment and the first quantum mechanical device used to extract some kind of energy.
In this case, it's an engine to extract energy.
Yeah. Yeah.
So we have two bars and we want to extract energy from the hot bars.
Yeah, yeah. Well, the bats are maintaining this population inversion in order to extract the energy. And it turns out that the efficiency is less than the Carnot efficiency in this case. All right, any doubt on this? I think it's a pretty nice example to warm up. So that will cover the first point, the introduction. Let's move on to the what I call previous concepts to deal with the theory itself. Okay. Von Neumann was the one who set the foundations of quantum mechanics, relevant for even single particles, right? This will enable us to extend all the ideas of thermodynamics to quantum systems, mathematically speaking. So you just need a system, define a system, and some kind of environment to interact with. So the main point is basically that observables are Hermitian operators in space. You can define some operators in this space. Okay. Then the states will be described by a density matrix, let's call it rho, which are positive operators with trace 1. You know, the relation between the state of a system and the density matrix is basically this one, right? That's the definition of a density matrix. And obviously, this is the normalization condition for the density matrix. Again, if you want to have the average value of a given operator rho, it will simply be given by the trace of rho O. Okay? It's basically what we will use in case you don't know this. For a closed system, non-interacting with the surroundings, the temporal evolution of the density matrix is given by the von Neumann equation, which is basically the Schrödinger equation for the density matrix formalism. It's straightforward to derive, right? Imagine you have this. It will be given by the time derivative of this, which is the same as this one plus the other term, and then recalling the Schrödinger equation, you have Schrödinger. Then the first term become minus I h bar h and then for the second term it's simply the Hermitian conjugate which is basically nothing there. Signs are okay, right? There you go. So, in order to solve this, the solution can be stated in terms of a unitary operator, U, T0, so that the density matrix at a given time will be equal to U the initial time, and then where this U t0 is equal to the time order of the exponential of minus I or h bar integral of t0 to t h Alright? That's a temporal evolution of any density matrix given the von Neumann equation. Everything arrived, okay? Von Neumann also introduced the concept of the von Neumann entropy of a density matrix, which is defined as minus, okay, so B, the trace of rho logarithm of rho, and if one decomposes the density matrix in a base of the in its eigenbasis, we can write simply minus case B sum over I, lambda I, and logarithm of lambda I. Okay? Since we are interested in thermal states at a given temperature, one defines the thermal states in quantum systems as the given states like we do in statistical mechanics, right? 1 over z being set the partition function where it's simply a normalization condition and then the exponential of minus the inverse temperature times the Hamiltonian of the system. Okay. All this is for closed systems. We are interested in system interacting with the surroundings. In order to do that, mathematically one extends this equation to a more general one called the Lindblad equation, Lindblad-Master equation. There are other names there, but yeah, Lindblad-Master equation. I do recommend you to take a look at Danny's notes on this, and you can find the derivation there. It's basically if you have a system weakly coupled with a thermal bath, the Markovian solution in this case will be given by an equation of this kind. Here you have the von Neumann equation plus some kind of extra terms, dissipative terms of interaction between the system and the environment. These d of rho are given by this expression. Okay, this gamma are called the rates. Okay, the rates of, interaction rates between the system and the environment, and you have this Li dagger called the jump operators, which are modeling the interaction between these two systems. This I goes 1 to n, being the number of paths you have your system coupled with. Okay. Obviously, if there are no coupled paths, these gammas will be 0, and one will recover the von Neumann equation. Simply as that. This equation is really difficult to solve analytically. One usually tries to do it numerically, but sometimes you are interested in the steady state. So for the steady state, the system doesn't evolve anymore. So the derivative is 0, and then one gets a simplified version of the Limber equation. Okay, that's even simpler to understand. There is another way to write this down, which is basically by terms of a super operator, because the symmetric is an operator. You can define an operator acting on operators called the Liouvillean of the system. Okay. In fact, you can know this only by knowing the Liouvillean, because it's basically how it's acting over a given state. Okay. Another important thing to note is that if you have thermal baths attached to your system, these gammas must obey some kind of a relation. Imagine you have your system coupled to a bath with several constant gammas. The relation is called the detail balance relation, and it's basically nothing there. It's something you will use if you do this numerically, or you want to solve this for this simple case. You need to take into account that the relation of the gammas must be this one.
What's the significance of gamma plus and gamma minus?
Yeah, it's the rates of.
So in that equation, how do they appear?
Yeah,
How?
The gamma,
the gammas here.
gamma,
Yeah.
and up is when you increase
Exactly.
the
Okay.
level, and down is when you
Okay.
Exactly.
when you
Yeah, both directions.
When you
Emit and exit. Okay.
Yeah, both directions. Okay. There's another way to write this down, which is basically using the Bose-Einstein relation, which is you can write this down as 1 over where this nth is given by a to the minus beta h bar omega minus 1. It's plus here. That's Bose-Einstein relation for the baths in case of the bosonic baths, which is the usual case. This gamma is simply a constant you define. So everything clear here. These are the main tools you deal with when analyzing quantum thermodynamical systems, especially temporal evolution of systems. Okay, you simply need an extra version, more difficult shape of the Liouvillean equation, and add extra terms, taking the dissipative terms, and you also need to take into account the thermal, the shape they have, the thermal states, and the shape of the rates, if you want to model this kind of thermal baths. You can also use other baths modeled in different ways. Okay? Okay. Let's move on to the third point, which are the laws of quantum thermodynamics. So we're going to do it in a constructive way. We'll consider first a closed system, not interacting with the environment, and then the other way around, a system interacting with the environment by a different way, we'll see. And then we'll mix all of them to get to the first law of quantum thermodynamics. So, first of all, consider an isolated system, which in the quantum mechanical world means unitary evolution, or the evolution given by the Liouville equation. So you can define the internal energy of your system simply as the average of the Hamiltonian, is simply the trace of your Hamiltonian, and the state of your system, density matrix. You can do it that way. So since it's isolated, thermodynamics tells us that every energy change will be ready to work. So if you compute the variation of energy, this will be equal, I will assume T0 equals 0 for the rest of the explanation. So you will have the derivative the same. Since you have two terms, you'll have something like trace or dot T prime and the second term okay. Here we said it's the evolution is unitary, it's an isolated system, so this will mean I will also make h bar equal to 1. Rho dot will be given by the Liouville equation, so you can substitute there first term, and the second one is minus psi Since we don't know the shape, neither of the Hamiltonian nor the density matrix, it remains the same. But the second one, you have the trace of h, and then here h rho or rho h. This will be equal to 0 because of the cyclic property of the trace. So this will cancel out. And you get that term, which is the definition of quantum work. Okay, you want to clarify this better? Okay. So you have this isolated system. You can model it with a unitary evolution, aka the Vivid equation, and you get to this expression for the work, which is related to the change in the Hamiltonian. Okay, so every energy change is equal to work for isolated systems. The physical idea behind this is that since you can control the Hamiltonian externally, you can make some kind of a link between that and work.
So if your Hamiltonian is time independent, you cannot get work.
Exactly.
So for this case, that is isolated,
Yeah.
if the Hamiltonian is time independent, you don't get any change in the energy.
Yeah,
Yeah.
exactly. So that's what I'm saying. So you need the spectrum essentially of the Hamiltonian to change with time.
Yeah. Okay. Good. Let's move on to another scenario.
This is a bit strange, no? So if I have a part, so imagine in the Ramsey scheme, I have a particle prepared in the plastic and I have a
Yeah.
sigma z rotation, it's time independent, I mean this thing is rotating,
Yeah.
so
Yeah, it has many flaws.
okay.
As you can see, I pointed out this definition of work.
Well, no, I would say it has many flaws, but not this one.
But what, I mean, if an electron going around an atom,
It doesn't perform and work, does it?
why?
Because there is no change in the energy.
Ah, I see, okay.
Hmm.
That's true, there's no torque, okay.
I
There's no
mean,
change.
it's talking in this sense of motion and it's very complicated.
Yeah.
But usually if you have a system, any system, and the energy doesn't change, you assume that there is no intention of work or
Okay,
heat
I
or
see.
whatever.
So if I have the electron orbiting the hydrogen atom in one energy state,
Mhm.
you say there's no energy there. But if I jump now into another one,
Exactly,
then this would be energy, right?
exactly.
Because then, okay.
Yeah.
Okay, because then there's a changing torque. Okay.
So that's for the isolated system. Let's move on to a different kind of layout. Right now we have a Hamiltonian which is not time dependent. Okay? But you have your system connected to some kind of a bath. Okay? Now the definitions of energy will remain equal, right? And you can compute the energy difference. So we'll have something similar to that. Again, applying the rule. This will be equal to 0 since Hamilton is not changing in time. Plus now we have an open system interacting with a bath. We cannot use this equation anymore. We need the Limrad equation, of course. So let's plug that in here. Have the trace of H remains the same, and then rho dot. Take a look at that, the fact that we have two terms here. The first one is something with a Hamiltonian. When we do the trace, it will cancel out. It's the same situation here, but we do have an extra term, right? Okay, we get to a similar expression to that one. In this case, we have identified everything with work as it's isolated. Now, this connected to a thermal bath, etc., we will associate this with heat. Okay, that's the definition of heat in quantum thermodynamics. It's basically the energy difference related to the change of my state of my system. This is a simple case with the Hamiltonian remaining equal. But yeah, this is the definition of heat. Just similar fashion to that one. I point out the fact that this is a definition. Okay? No doubts, right? Let's move on to the general case where we have baths and work surfaces. Imagine you have a system attached to a bath, that one, and then some kind of a work source which can be modeled by a battery, for example. There is something providing you with some work. It's a battery. Okay? So let's analyze the energy change. I'm going to use the differential notation instead of integrating that. We'll do that later. So you have again a trace of rho of t, h of t, and this will give you two terms. One of them is the trace of rho dot of t, h of t, plus the trace of rho of t, h dot t. This first term is exactly the one as this one. Concretely, it's the derivative of the one, so this is the heat flux, right? Simply take derivative here, you get to that expression. And in a similar fashion, you can have the derivative of the work there, a work flux or the power, as you can name it. So here you have the first law in the quantum regime. Every energy change in my system can be expressed as a sum of a heat term plus a work term. Something you can control, you can model. In this case, it's defined via a Hamiltonian change. A change in Hamiltonian, it will affect your system in any way, and will be given to work. With work, sorry, giving away work. And then the thing that's left in your energy balance, it's heat. Something you cannot control related to the change of your system. Okay, with a dissipator, for example. I'd like to point out that it is assumed that the system and the bath are initially uncorrelated or weakly coupled. So the total density matrix of both systems can be written in this way. Or if your bath is thermal, it will be given, this is for the initial time, this will be given by a Gibbs state at a given temperature, right? Well, I will in the case you have a multiple bath scheme, imagine here instead of having one, you have V2, V3, etc. This by multiple copies of the thermal bath. The only condition they must satisfy is that when you apply the dissipator of a correspondent bath to the thermal state of that bath, this must be equal to 0, right? That's the condition for the baths, the state of the baths. Okay, so for I. Okay, everything clear? Simply we just wrote down the first law. Yeah, different way.
But again, this depends on you defining these two quantities in this way.
Yeah.
So, okay, just generally, are there other formulations, quantum formulations of the first law? Definitions are different?
Well, in general, you can always write down these like this, right? It's a sum, a mathematical sum.
Yeah,
but
the distinction. That's
what you include here and here might be different than this or that thing. That's the point. Or the way you compute this W, instead of having that thing, you can use another scheme, like a 2-point measure scheme. Yeah, it's different approaches.
And what if I don't have the assumption that initially the system is
that's another theory. Okay. Strong coupling is a different thing. We won't cover that here.
Has anyone thought, okay, I can think of, then if I don't have that assumption,
yeah,
the separability assumption, I can treat the system and the path as one system, closed. I can define whatever the unitary is on this, and then I can start tracing out things, and then using this approach, is there a way that I can derive a consistent first law?
For first law, I really don't know, but for second law, we will do something similar the following day. For the second law, we will get the expression for the entropy production simply by tracing out degrees of freedom.
Okay.
It's a very nice derivation.
I know this one.
You know it.
Because normally this is the standard treatment.
Yeah,
so I can do this as a standard assumption.
Yeah.
I close everything and then I decide what to throw.
Yeah, exactly.
Okay.
I would like to point out that some people call this thing here, the fact that you can separate this, the zeroth law of quantum thermodynamics. Okay? Check.
But this is the farthest you can be from a law.
It is
It is an assumption that you do.
It is it's not even.
Yeah, law is something that always fulfills.
Yeah.
And this is as
Some
assumption that you do that
Yeah.
almost never fulfills.
Yeah, basically they say if you have a system at equilibrium, it remains in equilibrium, right? If you have two systems in equilibrium, they remain in equilibrium since they are separate. There are no energy fluxes between them.
One thing is to be at equilibrium, another thing is to be separate.
Yes.
And also it's not true that if you are separate, you will remain separate.
Yeah, for sure. Yeah, that
I would
say
expect something which is
some people.
to be some sort of transitive property like in classical.
Yes, exactly. If A is in equilibrium with B and B is C, then
I think since we don't have a proper definition of temperature in quantum system, they came up with this kind of exoteric stuff. So you can take a look at the review by Ronnie Kozlov in 2013, where he stated this. So what time is it?
It is actually 2 minutes to 2.
So we're going to perfect. We're going to finish here because the next step is dealing with the second law, and I think that presenting it and then moving to the following point won't be good. So I think it's better to continue. That's well. Okay. So see you next Friday, and yeah, thanks for coming. Yeah.